we got to modeling polarons. And so I never introduced the model before, so this is the atomistic model that we use for our calculations. And so it's a perovskite unit or lattice essentially, so 2 by 2 by 2 lattice with a certain number of atoms. And then to passivate the surface trap states, or like this would be very stable by itself and needs a surfactant. And so we just terminate each of the surface leads with a certain type of ligand, which counterbalances the charge. And same for the bromides. And these ligands correspond to what's seen experimentally. So this would be like oleic acid and oleoamine if you do experiments. And so we have a total number of atoms of about 1,000 and 2,800 electrons, so it's a very massive model. It takes quite a bit of computational power. And just a note on how we do our calculations. So we use VAST software, being no heavy initial software, and VAST uses periodic boundary conditions. So by default, it uses plane waves, which describe the valence electron, but it uses pseudopotentials to describe core electrons. And then we use a PV functional.
Periodic boundary conditions. These are a bit of vacuum, right?
Oh yeah. So it's seven angstroms of vacuum. So it's so it should be decoupled from each other.
Say 7 inches of vacuum.
7 angstroms. On the monitor, it looks like inches.
7 feet of vacuum.
And so we optimize it, do calculations, and so this is what the corresponding density states for this model looks like. And so compared to the particle in the box, or approximate particle in the box that was up earlier, you see that these near the band edges, it shows kind of distinct peaks, which are similar to S, P, and D bands. So that's what these the labels correspond to. So S, P, and H for the hole, then vice versa for the electron. And for the rest of the presentation, the important thing to notice is for the conduction band, it has a very sparse or very low density states near the band edge. And that's due to a very strong spin-orbit coupling. So if you don't include spin-orbit, it reduces the band gap by 0.7. So basically it just takes the density states I have there and spreads them out even over larger energy states.
Just because there's predominantly P state from bromine.
Yeah, or from the lead. So all the conduction band states are lead P, or 6 PMs, and they have very high angular momentum, so they have...
Yeah, because spin-orbit effects is strongest, not as strong with the P orbitals.
Mm-hmm. So, they have low density states, and the energy difference between this SE and PE states is about, for our model, is about 2 EV subgaps, so that's fairly large. Because if you consider thermal energy, it's about 30 milli-EV, I guess 25 EV. Yeah, so this would be 200 milli-EV, so thermal energy is going to be smaller than that. So you would anticipate that you might see slower cooling just because you have a mismatch between thermal energy to populate that state and the subgap that's there.
So here, so you consider this state as polaron states?
No, this is charge neutral. So this is
No polaron yet.
yeah. So
Okay.
so this is work that we've already published. So just a charge neutral model, and then we're working towards the polaron. So it'll be a couple more slides for the polaron,
Okay.
and then so it's a ground state electronic structure, and then just to make the connection back to particle in the box. So in this left, so this box represents like the boundary conditions, and this sphere on the inside represents the envelope function for a particle in the box, and we don't compute the periodic parts or the fast varying. But for ab initio calculations, you look at the orbital, so this is the corresponding orbital for the lowest excited state. You can see like the plane or the standing wave in the symmetry in here. So this is the model in 3D. So and then what this figure shows is the density just projected on the 2D. So we just integrate over x and y. You can see this would be the U potential here, and then it's not plotted, but you can imagine an envelope function that goes around that. And so, yeah, it's just helpful to know that at least some of the orbitals in these models obey like symmetry, and symmetry is kind of important because you can kind of have a guess of what transitions and some properties of these materials will look like, or what would happen just based on symmetry. And so that's ground state. And so we'll move on to excited state dynamics for this model. We'll just have one slide on it. So there's a lot going on here, but basically what this figure represents is the carrier cooling in time. So this is a log scale, so -3 represents 1 femtosecond, and 0 is 1 picosecond. So that's usually the time scale that cooling occurs on. And the green represents charge neutral background, so just the ground state. The yellow represents non-equilibrium charge density, so you have a photoexcited electron, and blue represents hole density at these energy states, and the lines just correspond to energy expectation values due to changes in population over time. And so for both these models, we see fairly fast hole cooling. It occurs on 100 femtosecond time scales, and that's kind of in line with what they see in experiment. So, but the most interesting aspect of this figure, it's kind of hard to see on this fake background, but you kind of see a smear as it cools down here, and that kind of indicates that there's population buildup or density buildup as it's trying to cool to the band edge. And so a better way to represent what this plot is, we move it over to this plot. And so this is just a dimensionless energy, so 0 to 1, same time axes. And then this plot here just represents the density of states, or just bands for the model. And what's plotted is a single exponential fit. If you just try to fit the decays to a single exponential, and that's the red dotted line. And if you compare that to what's actually computed, over here we see that there's a fairly faster than normal or single exponential decay. And then it gets to a certain point near the band edge, and this decay slows down considerably. And we attribute that to the large mismatch in density states, or a large slope gap, because thermal energy is going to be much smaller than this gap, so it's going to take a lot longer for it to cool to the band edges. And so that was interesting in itself. Dimitri mentioned we published that in JAX earlier this year. But then if you consider where these density of states are, the energy spacing, and the fact that we have slower non-radiative cooling, an interesting idea would be to utilize this state here and try to manipulate it into being an emitting state. Since you have a buildup, you have inverse occupations, you could potentially get optical transitions or photoluminescence there. And so that's where we move on to modeling polarons for these models. And so the two models that we'll be talking about here for today are just positive and negative, so just adding or removing charges to our quantum dot model. And so, and for each model, we break it up into 3 submodels. And so if you remove one charge for the positive polar, you can get a doublet state, so you have an unpaired spin, which is a doublet. If you remove 2 charges, you can get singlets, so it's 2 spins align anti-parallel, and triplets where the spins align. And then same idea with negative polar. Add 1 charge, doublet, add 2, you can have singlet or triplet. And so this is the ground state electronic structure for the positive polar. And so this is the whole density states for the whole model. And this boxed off region is what corresponds to here. So we want to look at valence bands, because that's where the hole is going to be. And so you can see in each of these figures, so singlet, doublet, and triplet, the filled in regions correspond to occupied states, and then these white figures below the line correspond to unoccupied. So that's where the hole is going to be for both these models. And then we can see the same, or kind of see the same possible symmetry states. So you could expect that your polaron orbitals will see some sort of symmetry as well. And so that's what the density of states look like. And this figure here shows the computed IR spectra. So between possible optical transitions within these regions. And we plot them in wave numbers. So lower energy is to the right, higher energy is to the left. And so the lowest energy transition for all these models are indicated with the arrows. And we see for the singlet and the triplet, they're basically the same for lowest energy transition. So they're fairly bright, whereas for the doublet, the lowest energy is fairly dark and it's higher in energy. So if we were going to look for P alpha in the systems, it would probably be from the singlet or triplet models compared to the doublet. And basically the same figures, but for a negative polaron. So instead of looking at valence band, we look at conduction band occupation. So for singlet and triplet, we see the occupied regions. For doublet, it's half filled. And the reason it's half filled is each band is twice degenerate. So it takes two charges to fill up that state. And we look at IR absorption again for these materials. So previously it was at like 500 wave numbers. These are a bit higher in energy for the lowest energy transitions. We see singlet, triplet are about the same, again, in intensity and energy. And the doublet is about the same energy, but it's lower in intensity. Again. So it's kind of masked there. But so we see the same trend again, where we're going to see photoluminescence. It would probably be from the triplet or doublet configurations. And then for the last couple of minutes, we'll look at the dynamics for these polaron models. And so these are similar green figures as before that we saw. So they just correspond to polaron cooling. And so I put these visualizations here to kind of help interpret what we're trying to model for these. So we can imagine that we inject a hole, like we hook up some sort of molecular lead, and we just put it in a hole to the valence band. And eventually that hole is going to cool to that relaxed excited state for the polaron and be pretty stable there for a while. And we see for both of these models that the cooling occurs pretty much on the same time scale, a couple hundred femtoseconds. Hundreds of femtoseconds. And so we see cooling to the relaxed excited state. And then our next figure is going to be looking at time resolved and time integrated emission along that excited state trajectory. So it's the same cooling dynamics, except instead of non-radiative transitions, we look at radiative transitions that compete with it. And so if you have radiative transitions that's quicker than the non-radiative, you get counts essentially in this time result spectrum. And we see that early on in the dynamics, both the models, they show a cascading, or three separate bands of emission for these states with varying intensity. And you can kind of interpret that as you inject the charge, and then you have cascading of possible optical transitions, and then as you cool further down in the band, you essentially are just left with one optical transition, and that's what we see here. So this is cooling to the relaxed excited state, and then just emitting until the non-radiative, up to the non-radiative recombination time scale. And so the main difference between the singlet and the doublet is the singlet, once it cools to the relaxed excited state, the band gap is about 0.1 eV, and it emits there. Whereas for the doublet, it cools and its lowest energy transition is 0 eV. So it doesn't really emit from 0 eV. And so all we see is just the cascading low intensity transition when it cools. And so the last slide is, so if we consider how efficient these positive polaron emitters are. And so that's just summed up in this table. So this column corresponds to the radiative lifetimes, which just come from Einstein coefficients. And they occur, and their rates occur on the inverse microsecond scale. Whereas for the non-radiative transitions, for that lowest energy transition, they correspond on inverse picoseconds. And so essentially, if you just think about how to calculate photoluminescence quantum yield, it's the radiative over the sum of radiative and non-radiative. And since the non-radiative is 6 order magnitudes quicker, you have a very large denominator, and so you have essentially 0 photoluminescence quantum yield. And so that just kind of shows that if we're going to see IR emission, it's probably going to come from the negative polar, which is kind of what we suspected earlier. It's kind of leading into this project. And so, just to conclude, so the previous result we saw there was slow hot electron cooling near the bandits. That kind of gave the motivation to use that subgap that caused the slow cooling as an IR source. And just from ground state calculations for the polaron, we see that we do see bright optical transitions for singlet and doublet. So it does seem possible that we can get photoluminescence from the states if the kinetics match up right. But for the positive polaron, it's very inefficient, and we have ongoing calculations for the negative polaron, and we're working towards the charge neutral photoexcited polaron. And looks like I can time that out pretty well.
Okay, that sounds good.
And the paper is open for discussion.
So I try to understand it in terms of the language for physics. So the polaron you're talking about some defect level at about 0.2 eV below the valence band, condensation band minimum, and above the valence band maximum, right? So the level is not deep, but it's not shallow, but it's deep enough so that it's the value is much bigger than the thermal energy, right?
Mm-hmm. Yep.
So by carrier cooling, you mean the carrier gets trapped at that defect level, and it's slowed down a little bit.
Mm-hmm.
That's what you mean by carrier cooling?
Mm-hmm.
Okay.
And so in the non-polaron picture, we call that slow cooling.
Mm-hmm.
But as soon as we change our model into considering polarons, that transition would become the non-radiative recombination. And so we try to utilize that slow cooling as a non-radiative for photoluminescence.
Can you repeat for me, the terminology? Positive polaron is a hole with a little bit of induced charge that grows from the wire, right?
Mm-hmm.
And same for the electron.
Mm-hmm. So that would be a negative electronic charge interacting with like a mean ionic field.
But if you look from far away, the charge of this whole conglomerate is less than the charge of the electron, right?
Yes,
Because
because
you lose some charge onto the
Screen.
screen. No, see, that's where I kind of. Well, that's okay. So, also, I'm a little bit confused about the following. So, when you do your when you run your density functional theory simulations combined with non-adiabatic couplings, I mean, everything that's going on is already there. Polarons are not, and you look at the K-air cooling and so on and so forth, and then you kind of switch gears and you talk about polars. I'm a little bit lost there. What changed?
So I guess it's just running the same machinery for our non-adiabatic couplings, but with just different charge occupations. So charge neutral, it's like we wouldn't have any occupancy in the conduction band when we do our calculations for non-adiabatic couplings. But when we do the polaron, we occupy the lowest conduction band state, and then do the same.
And when
Machinery.
You say, when you say neutral, what do you have? I'm still a little confused here. I mean, I thought, okay, you occupy hole, there's a hole and there's an electron,
Mhm.
and you let it, evolve with time. It interacts with the thermal motion of ions, and whatever way it will, should there be polarons or not, it's all there.
Can I add a comment that you probably
Of course.
translate between two languages? If one is approaching computational modeling of a molecule or material, at the first step, one assumes that number of electrons in the modeling is equal to the total positive charge of all ions.
Well, assuming that the material is neutral, right?
But there is an option to change total number of electrons and recompute both ground state, dynamics, some excited state properties in presence of charge imbalance.
Right. And that stands for, this, for the excited electron and the hole is who knows where, we don't know anything about.
It doesn't need to be photoexcited. It can be injected charge.
Oh, okay, so you're not talking about for the excitation. Okay.
Not yet, anyway. We're working towards the photo
So
excitation.
it's just an electron moving through this quantum dot.
And getting dressed in a coat of phonons, if you want to be very theoretical.
So in the case of nanocrystal, you have something that you can polaron. Do you also have polaron in the case of a bulk crystal?
Mm-hmm. Yeah, but it's just, the polaron is just intrinsic to the polar crystal structure itself. So no matter what dimensionality, in some sense, you would expect, there's a possibility to see polaron
Okay.
formation. I guess it hasn't been experimentally shown in perovskite nanocrystals yet, but there's some evidence, well, at least to me that seems kind of useful to think that there's polaron occupations there.
You may want to check it with calculation. Because I'm thinking about whether, when you go to small system, because of the quantum confinement effect, whether the wave function is more localized when you pull out one electron or you add one electron into the system.
So yeah, these would be small polarons compared to what would be seen experimentally. But I guess, I don't know, it's the best we can do.
I'm not talking about the size of the system in your calculation, because it's 1,000 atom and more than 2,000 electron. I think that's enough for us to do it. But I'm thinking about when you go to a smaller system, nanocrystal, because of the confinement effect, the subgap space, the polaron state, can be more localized than in the bulk, and that's something you may want to look at.
You're correct, but it is like art of possible. So if one would consider, if you permit me to comment, if one would consider polaron in the periodic bulk material, then one needs to take into account non-zero momentum. It will be traveling polaron, which adds additional degree of freedom. So one needs to, if doing like periodic boundary condition calculations, one needs to recompute it at different k points, and it will be much better.
It doesn't have to. It doesn't have to. I'm thinking about some transition metal oxide. If you pull out one electron, you can see a small polaron almost right away across.
That's correct, but in this material it will be traveling polaron.
Yeah. Because in this case you may not have a small polaron, but you have a large polaron, and you may need to deal with a very good system. Yeah.
Sorry to ask so many questions. I'm really curious. Very interesting work. Can you please show your conclusion slide?
almost there. Okay.
Okay, due to blah blah blah, we try to utilize Lars sub-Gale as an IR emission source. Can you please briefly repeat for me? I'm just kind of missing the idea here. What recombines with what? A particle has to recombine with a whole, right? At the rate of 40.
Mm-hmm.
No.
No.
Let me translate once again. So, common vision of emitting semiconductors that they emit because of the particle and whole radiatively recombine from conduction band to valence band for neutral system.
Mm-hmm.
If the system is charged, if the either positive or negative charge is injected, then it will be recombination of particle and whole, but their energy offset will be much less. It will be for positive polaron, the particle will be on the top of the valence band, and whole will be like next state on the top of the valence band.
Okay, I see.
Okay.
You know, a couple of years ago, essentially the same authors were going perovskite for photovoltaics, perovskite for photovoltaics. That requires very poor ignition, right? You don't want them to emit the light they absorb. And now all of a sudden the same authors go perovskite for LFDs, perovskite for LFDs, which is what changed? Is it the confinement? What changes the properties? Cold, so much.
There's definitely the confinement effect. Because I guess the photovoltaics, perovskites, like just thin films, they came across those.
Can you go to the slide where I introduce the model?
This one?
Yeah.
Yeah, so thin films, I think people got interested in those by the good results in like 2009, 2010 range. And so there's a big push to use those for photovoltaics, just due to the very long non-radiative lifetimes they have. But then these nanocrystals were initially made in 2015. That was the first time they were synthesized. And that's where they realized the wide color gamut, or like high color purity they have. And so that's where the LED idea came behind. So make films of nanocrystals instead of bulk film.
So it comes from careful tapping of surface sites with this carefully chosen ribbons. Are there more questions? More questions 1, more questions 2, more questions 3. If no, let's thank the speaker and and session is closed. Let's adjourn.